Okay, as we migrate into talking about acids and bases, this is one of the most critical concepts in all of chemistry, and it really carries through at the core understanding of chemistry through organic chemistry, biochemistry, etc. It's really the most important idea, and we're going to start with the simplest definition of acids and bases called the Bronsted Lowry definition. We're going to think about writing out the equations, see what happens when we allow those to react with water, write those out. We'll think about equilibrium constants and equilibria, and then we'll talk a little bit about amphiprotic substances. There's lots of different definitions for acids and bases. Then the simplest one that we're going to start with is the Bronsted Lowry definition. And in that construct, an acid is anything that donates an H+. We'll call this also a proton because if this is a hydrogen ion, it means it's a proton or an electron, but if it's positively charged, it doesn't have the electron, so really it's just a proton. So I'll use that language interchangeably. In contrast, then, a base is anything that accepts that H plus or that proton. So in the generic reaction here where we have HA plus B, we have an acid and a base. The H here, this proton, is going to leave and it's going to be accepted by the base, and now we have BH plus because of that H plus, and we have the anion over on this side. And what's nice about this is you can see on the reactant and the product side what has been converted into what. And so if we start with the acid, the HA, on the left side, we see that it loses its proton because it donates it, that's the definition, and it forms A minus. We call these conjugate pairs. So this is the acid, and over here A minus is the conjugate base. Because now if you imagine thinking about these as the reactants and letting the reaction run from right to left, this would have to act as the base because it can only accept a proton. It doesn't have a proton that it can donate. Similarly, B is now BH plus. That's the conjugate acid of the original base. Same idea is illustrated here in this little cartoon. So start with looking at the reaction, which is the bottom half of this figure, and you have water, which water can act as an acid or a base. We'll talk a lot about that. In this case, it's acting as an acid, and you can see it's connected over here with its conjugate base, which is just water minus that proton, because that proton was donated to the base, in this case NH3 or ammonia, to make NH4. And so on the top half of this figure, they're showing you here the conjugate acid-base pair of water and hydroxide, simply because of that removal of the proton. And then the opposite of that, the conjugate acid-base pair of the base and NH4, this case the conjugate acid, because it's accepting that proton. Protons, if they're being removed or donated by something, they have to go somewhere. So that means anytime there's an acid in the system, there has to be a corresponding base to accept that proton. So as I mentioned, water can act as an acid or a base. That's the miracle of water and why everything exists within water. Here's an example of water acting as a base. So here we have HF, this is hydrofluoric acid, reacting with water as a base. And in our Bronsted Lowry definition, we know that the acid is going to dump that proton, and it has to go somewhere to the base here. And so the acid-base conjugate pairs are color-coded. So we have water as the base, and its corresponding conjugate acid is H3O plus, simply because it accepted that proton. So what's nice about this figure is it's showing you explicitly the Lewis dot structure, so you can see what's happening with the electrons. Now remember, in Lewis acid, or in Lewis structures, the straight line represents two shared electrons in a covalent bond. So when this proton in HF, the acid, when it leaves, those two electrons are going to stay with this fluorine, which is why all the way over here you see those two blue electrons. They stayed, and that's what makes H positive when it leaves. Sort of in contrast here, for water, it's got those two lone pairs there, and so the new bond forms because H didn't take those electrons, and now you have this H3O plus. We also call this the hydronium ion. Since water can act as an acid or a base, we give it a special name. We call it amphiprotic. Amphiprotic means that it can either accept or donate protons. So let's work through a couple examples as practice, starting with H2SO4, which has a common name of sulfuric acid. So there's a couple different ways that we can write this. We can look at this and say H2SO4, okay, well it's got these protons here, so I'm going to probably call this an acid. And we can write it out. We can write that dissociation of this acid into its corresponding ions a couple different ways. First way is sort of the implicit way, which just takes this molecule of H2SO4 and breaks it into the acid and base correspondingly. And so if the H2SO4 gets rid of that proton, we can write it in that there's just a free proton hanging out here. So this is the acid. This would then be the corresponding conjugate base, which we can circle just for clarity, and we're left with this proton here. But as I mentioned, this is an implied way to write this because, as I mentioned before, H plus, it has to go somewhere, right? It's not just hanging out. And so the more explicit way to write this is to include water in the reaction as the conjugate base, or as the accepting base. So this is the explicit way to write this in green. These are both correct. Often people write this shorthand as in the first reaction, but you can notice that it's missing the thing that's actually accepting the proton. And so here I'm being clear that, well, water is the thing that's going to accept the proton. So H2SO4 is the acid. Water then is the corresponding base in that reaction. It accepts the proton. It creates H3O plus, which is the conjugate acid. And of course, HSO4 minus is the same conjugate base we had in the first. So HSO4 minus is interesting because it's an amphoprotic or amphoteric, those are sort of interchangeable words, molecule, because it still has one of these hydrogen ions left over. So it could donate it, acting like an acid, or of course it could just run the reaction in reverse, accept that proton and become H2SO4, which means it's also a base. That's what the definition of amphoprotic means. So let's write out, very similarly that we did with H2SO4, let's write out what it would look like implicitly if we didn't include water and we just said let's have H2SO4 minus act as an acid and then write it implicitly with water. So pause the video, see if you can write that out. Okay, so hopefully we get something that looks similar to this. So the implicit form, we just dump that proton here, so HSO4 minus acting like the acid. It liberates that proton. In doing so, it creates the conjugate base, which I've circled here, SO42 minus, which we know sort of generally as the sulfate ion. We write that implicitly with a base, so HSO4, the acid, reacts with the base water. That means the water is accepting the proton. It creates the conjugate acid, H3O+, just as it did before, now leaving us with the sulfate anion.